Then the symmetric ones are the point symmetry on the x-axis. Okay, so you have perfect symmetry, then these points would be like each is just apart. We have the same one. You get perfect symmetry. If you cut it out, open the rest of it. In this case, the median and mean will be about the same, right? The sample median will be approximately the same. And this is a peak distribution you could have, bell shape. But then you could have skew distributions. This would be right skewed. Okay, the bell is to the right. You could have less skewed distributions. Okay. So there's some nomenclature, we could use it. For this, what would you say? It's really sort of uniform in the middle. You don't have that much data on it. You've got to be very careful. You draw conclusions. Symmetric or skewed. Actually, if you said symmetric, I go along with it. I don't, you have outliers. You don't have that long scale. Now we talked about the five descriptive statistics or the starting set, right? Let's just get into this case. You can just pick them off this. It's one nice thing about SIM. So we have minutes, number 2, we theta, hat. So the min is 18, right? And the maximum is median. You have a partial order today. Just add 2 columns to the frequency, which you won't probably want to do too. Do that. And then the cumulative difference. Here you just add up. You have 2 down supplemental in this class. 3 here. By the time you get to the 70, you're up to what? 7. 11, 14, 18, 22, 25. And that should be your sample size. Well, in this case, the median would be the average of the 15th and 16th order statistics, right? And we have 15 down to the end of this class. So the 15th order statistic is 98, not 90. Okay. The stems are not in order. I mean, the stems are in order, these aren't. So the 15th order data point is 98. And the 16th order data point will only one of these. The Is that clear? So we think about the median immediately. Data hat's going to be 1/2 of 98, right? Plus 105. What? 101.5. And then the other, that's the half the data is less than that, and half the data is greater than that. It's always a nice descriptive statistic. It's very robust. Okay, how much data do you have to send to infinity to kill the median? You have to send about 50% of the data. The median won't budge. You could move all these points. I could replace all these points here by infinity. The median won't change. So it's a very robust estimate. It's very insensitive to any outliers. Then we have the first quartile you could think of as the bottom median, but I don't want to do it that way. And also there's some elaborate rules for quartiles. In class, when we do a quartile, we just divide n by 4. If it's not an integer, I round up, and I just pick off that order. So I don't do any elaborate rules in class. We're going to be using a computer anyways. It's going to have its own rule for quartiles. So in this case, n is 30. 30 divided by 4 is 7.5. I'm just going to pick the 8th order data. Okay. And I have 7 data points down through this class. The 8th order data point is the smallest one in this class, which is this 8. So P1 is 80. And then how about the third quartile? I just go back. I just count up in order through 8. It will be, the 8th one will be the smallest one in this class. This one. Any questions on that? See, if you use a computer, it's probably going to, for the 8th, the first quartile, it's probably going to take 1/2, the 8th, 1/2 the 7th order data point, plus 1/2 the 8th. That's what the package is going to do. But in fact, we'll just, I'll just round up. Okay, now comes to the most important thing about these descriptive statistics. We want to declare outliers. Outliers are often the points of interest in the sample. Okay? They don't belong. Okay? There's been a lot of discoveries in science because someone looked at the outliers. Kepler came up with his elliptical orbits. He didn't know any calculus of it. He came up with that by all these observations, and he kept trying circles, and it didn't fit. He was worried about the outliers. So we kind of figured out these ellipses and that sort of thing. So, I mean, that's one discovery, but there's been many, many discoveries in science because someone puzzled over that. Now, this data has to measure a center, this median, right? And a measure of spread is the quartile range. P2 minus P1. This is like the basis of our outline. That gives you a spread in the data. And do standard deviations. It's about 1.3 standard deviations, approximately. This is a non-shape distribution. and that's like our spread that we use. And then we define this h, which is just 1.5 times I2. So that's 6. And then we have the lower fence. That's just V1 minus h. And the upper fence is 2 plus h. So then this would be 1 plus 60. Now, anything inside the fences is not an outlier. Anything outside the fences is a potential outlier. It might be just a dumb typographical error which you caught. My goodness, it's school. It could be, it's not too hard. In fact, the 18 is not too hard. But it's just outside the fence. So here, I add one more on the lower fence here, the upper fence. Then I'm ready to draw a box plot. Now, a box plot of the data, the box is the middle 50%, that's the quartz box. And then you put a symbol inside for the median. And then the ends of the box arrows down to adjacent points. Okay? Adjacent points are points, they're within the fence, but they're closest to the fence. That's where the tail ends. In this case, we do have an outlier. This 18 is an outlier. So I have an adjacent point on the lower end, and I use 52. Oops. Okay. So that's where my box plot is. And then the upper one, there are no outliers at the upper end. 156 is well within the fence. So there's no upper adjacent. Any questions so far? So now I'm ready to draw my box. And we'll be using this throughout the term. I really like box plots. So the box plot, you just draw a number line. It's got to contain the range of the view. So you can do it on the thing, just lay off. Put the box in first, 80 to 120. Go to the median end, median, and 125. And then draw the tail to the lower edge point, which is 52. Put the star into the outlier. Then the upper tail goes to the max. So no outlier, the max is 156. Any questions about that? Thanks. The box plot only contains data. Every mark on the box plot corresponds to a data point. These are the quartiles, or maybe the average. These are the quartiles. This is the median. There's my middle 50%. The middle 50% of the data goes from 80 to 120. That might be important if you have the middle 50% and you're trying to describe a distribution somewhere. Here's the point which is within the fence, but which is closest to the fence. And look at that gap to that outline. That's a huge gap. Okay? That's important. There's nothing around this outline. Even though the fence came down here, don't draw it to the fence. The fence is not a data point. No outline. It's sort of symmetrical. Right? You have an outline. Any questions on that? Box plots are great for comparison because you can just line them up. You can do it horizontally. You can do it vertically. I think R does it vertically. Minicab used to do it horizontally.
I think Minitab does it vertically unless you specify transpose.
Oh, okay.
And then it'll do it horizontally.
So if you were comparing 20 things, and that's not hard to do in a big experiment. You might be comparing 20 different things. So you have like 20 samples. If you have 2 samples, you can do back-to-back stem leaf plots. So that's very informative. If you have 20, you can't. But if you can line up 20 box plots across the page. We have another data set, and I want to do a comparison box plot. I have to have exactly the same number. We'll have it. Any questions on that? There's another plot that we do sometimes. Box plots are a bit dangerous when the sample size gets small, right? I can ruin the quartile with, if I move 26% of the data, I can destroy a quartile. It's not quite as a process. So if you have a really small sample size, you can quartile may be effective on that. So, there's another, let's do that. I don't have any minutes. Sometimes we have to bring them up at the same time. You travel enough to Any questions on okay, so let's begin some inference then. Most of the information in the sample is in the middle, right? And often you end up phrasing your questions of interest in terms of the middle. That's where you have information. You might be a little bit worried about the shape of the distribution, but if you've ever done any density estimation, in very large samples, like 200 to 500. So instead you say, well, I'll just think about the middle of the samples, and I'll compare samples by looking at the difference in middles, right? Difference in means, and I might even say a typical, you're doing something, you're taking these measurements, and you say that maybe it's blood pressure, and you say, well, a typical male has this as his blood pressure. And by typical, you're thinking of the mean, right? The middle, the median, and you have blood pressure medicine. A typical male on this blood pressure system, the difference between typical males, a typical male on medicine A, blood pressure is 10 units above a typical male on blood pressure B, 10 units above. That's probably the difference in means. And it goes on forever, which is impossible because it is just on. Shouldn't complain on that, but we end up losing the black can. Running on that whiteboard with those chemicals, which I hate. Yeah, it's the same thing. Just like the block goes back in and has to create. So again, we have a population, and we have some distribution here, and it's generating the data. And then we're going to use the data to try to estimate the center. And the parameter we pick on today is the median. So the goal is find the difference in the median. Now, what do we have to assume in the population? Really nothing. There's no assumptions. We just assume the population is continuous. That's really all we need. So it could be skewed, uniform, normal, double exponential, Cauchy, could be anything. Okay. There's no assumptions whatsoever. There's one place we'll have to make an assumption. Testing first. Now we do the key. Okay, let's do testing first. So we're focusing on a median, and we're going to test a population, the hypotheses about the median. So first we'll look at testing. Actually, one side will give you, it's more intuitive, then we'll do the two sides. So for testing, there's some value we want to test against. We'll do paired designs pretty soon. That motivates the test. Okay. For some reason, there's a standard you want to test against. You know, maybe you do have a new blood pressure medicine, and you know the median blood pressure. People on the standard medicine, they've been using this medicine for years, so we have a very good idea what the blood pressure is. You know, you might have a range of ages and things. That would be a simple illustration. Everything I can think of is like a two sample. You might have a lot of data on selling of houses last year or over the last 3 or 4 years. So you might know the median price of a house in the neighborhood. And then you decide, well, many things have improved in general. So take a sample of selling prices now, and then you want to compare that with the old median price. Then our statistic of interest is just, this is a sign test. That S is theta naught. There's a number of observations in our sample. Again, we have information. Which exceed theta naught. Okay, that's a sign test. It's very simple. You just count the number of observations varying theta naught. Okay, and if the number of observations varying theta naught is around n/2, why would you ever reject? That's about what you would expect if theta naught's the median of the population. So you have like a number line here. Here's n/2. So it's around here then. So what? Okay, now if the true population median's up here, then you're going to expect a lot over theta. Let's put some numbers on this. Theta naught's 10. Okay. Let's go back to the population. Here's an H population. And here's an alternative. Alternative is theta is very easy. So this is a function. Here's theta. Now, if H naught's true, this is where you're sampling from. about half the data is greater than theta naught, about half the data should be less than theta. It's the median. Right? Half the time, the probability here is a half. Now, the rejection rule is you reject H naught in favor of HA. That's the pointer to HA. Well, what's the HA picture? This is the HA picture. How many observations in your sample were in theta naught? 5. Here's your sample. Almost all of them will be greater than theta. So the indicator of HA is a big S. So you're going to reject H naught in favor of HA. If that's too long. You might just short this. Okay. So again, this is your number line. You know, how many do you want? This is your sample, okay? Again, there's going to be many. All these sample items are greater than theta naught. And then, again, how large is too large? Here's n over 2, okay? That's what you would expect under this. And then here's the k, okay? So you'd expect S to be around here under H naught, and you expect S to be around here under HA. K has got to be bigger than n over 2. And then how large is large? Type 1 error is all you need. Okay? Alpha is the probability under H naught that S of theta naught is greater than or equal to K. I just have to solve for K. And what's the solution? It's easy, right? What's the distribution of S? S is just counting up the number of observations which are over theta naught. It's a success if it's over. It's a failure if it's under. It's just counting up the number of successes. It's binomial under H naught. In fact, it's binomial under HA. But under H naught, the probability of success is a half. Half the time, an observation will be clearly mistaken. Okay, it's just a binomial with n trials and the probability of success going in. I didn't have to know anything about the distribution, the population. It could be normal, it could be double exponential, it could be Cauchy, it could be very skewed. It doesn't matter. There's nothing I have to, there's no assumptions I made on the population. And for this, to solve for this K, I don't have to know the population. Okay? Population. Well, specific. PDF. The population. Does not have to know. We say the sign test is under H. How about under HA? That you don't know, right? An HA picture, I scribbled over it, but I put it back up here. See, the theta I don't know. This is really the probability. Now I don't know what that is. That will depend on the gap here, and it will depend on the shape of the distribution. So under the alternative, you don't know that. But at least under H naught, you know the distribution, and that's all you need for p-values and setting up tests. Okay. Now let's just go to a p-value. Theta equal 9. Forget about it. So here's my samples of size 30. I want to know that because I should even say this up here. Under H naught, the expected value of this test statistic is n over 2. Observations over that. Go back to the data. I would go back to the standard leaf plot. It's easier. I just want to know the number over 90. Notice there is a 90 in that. There is a 90 here. So how do you classify that? Is it over or under? Actually, what we do is we throw out the 90. And our sample size goes down to 21. You might not like doing that, but then you don't have to worry about is it over or under. Okay. And then we just count the number over 90. So going back to this is what? It's 3 here. You can just do this. Or you just count up the frequencies, right? So there's 3 actually here. So there's 6, 10, 13, 15, 16, 18. There's 18 observations over 9. So, what did I say? 18. Now, is that too big? Always put down the null value so you know where you are. The last thing you want to do is make a dumb error. I'd like to say you're on the upside, that's where you should be. All right. And your p-value is probability of binomial n 29 now. P1 half is greater to okay. Now there's 2 ways you can find that p-value. You can go to the binomial distribution. You can use the package, which I can't do. What else could you do? How about just to have an idea where we are? Why don't we just standardize? Let's make it a z. You just have to, and for the z, you should use the continuity correction. Okay. So slow down. I'm going to use the Z. So I'm going to use the continuity fraction. I go to 17 and a half, right? I want to include 18. Then I subtract off my mean. And then I divide by my standard deviation. The mean is n times a half, and the standard deviation is, I'll just write it all down. It's n times a half times a half. So there's my Z value. It's 3. So 3 over the square root of 29. So let's count them. Any questions on that? Let's count. I don't have one. This is a Windows machine that's about 80 years old. It's Windows 1848. So I don't use it for minutes. It's 1.11. So I mean, you could use the normal tables. You look it up in the normal table. It should be 1 minus 8673. The p-value is fairly high. You're a good government person, so you're not going to reject that. So you would probably call it, we can always conclude like this, and that's what we do in this class. We failed to reject. 5%. Well, you could go back and look at your distribution of standard plot. It's right there. It's not a lot at all. It doesn't seem that odd. Okay, any questions on that? We'll be just using p-value. We're not going to set up a test. Now, if it was a two-sided test, suppose this was two-sided. We'll often be doing two-sided tests. We're going to reject it. Less than 90 is too small, right? Or too large. A number line really helps here. Just here's n over 2. L is going to be down here somewhere. K is going to be up here. Actually, P is 1/2. It's a symmetric binomial we use, so they will be equidistant. So that's the right picture. And what's the p-value? If you're on the upside, like we are in this problem, right? In our problem, sample S of 90 was 18. This was 29.2, 15. I'm sure you can put those on K's now. But here's 18, you're on the upside. So then the p-value is twice the probability binomial 29 1/2 is greater than 15. Let's say that S of 90 came out to be 10. You're on the downside, and the p-value is twice the probability of binomial is less than or equal to 10. Okay. Any questions on that? So if you were doing a two-sided test with our data, the p-value would be 26%. Right? 2 times 0.3. Of course, you remember, it didn't come out to be 10, so question on the sign test? It's our first test, non-parametric test, right? Non-parametric means, in this case, distribution free. Don't that makes any assumption. What's the downside? We'll come to the downside in a little bit. Okay, then what else would you guess?
Isn't the making the Mars test also non-parametric? It doesn't make that.
Oh yeah, it was non-parametric.
Okay.
Okay, let's do estimation and confidence intervals. Now, it's funny, if you're talking about normal theory statistics, it's often easier to think of the estimate and then go to the test. And at least in non-parametrics on it, for these simple procedures, it's the testing that's very intuitive, and it's the estimation where you have to think. Okay? And the estimate, I mean, you'll be really shocked when we get the answer. You're trying to estimate the median, but there have to be the sample median. And it doesn't in this case. It's just null value. What we do is we consider this like a process. We can graph it too. I don't think we have to in this class, at least at the moment. But that's our test statistic, and if you estimate the median based on the data, then you should never reject that value. In other words, we'll estimate theta by theta hat such that, oops, if I say yes, if I write ST, it means such that. When I stick theta hat and look at the number of observations bearing theta hat, that's what this is, it comes out to n/2. So what's the answer? You have one equation, one unknown. You can't solve it like you would in algebra. It's not a linear equation. Too bad. It's a sample median. If I stick in a sample median, that's always true. Because half the observations are above the median and half are below. So the median actually solves that equation. And if you go back to our example, if I pick on 101.5, then half the data is greater than that and half the data is less than that. And over 2 would be 15. So 15 data points are less than that, 15 data points are greater than that. Actually, it's between the 15th and the 16th, but it's almost n over 2. So you just, the median just chops the data in half. Half's less than half, and half's greater. So it's the most acceptable hypothesis. If you're so unfortunate that you picked your null hypotheses so that when you collected your data, the null hypotheses came out to be the sample median, well, you'll never reject H naught. Okay? If I would have tested theta equal to 101.5, I certainly wouldn't have rejected, all right? S would have been 15, p value, but two-sided test would be 1. It'd be 50% for one side. Okay, so there's our point estimate, it's the sample median. And I'm getting point for the hat. You've been in my stat class long enough. Should you screen it? What confidence interval is a point estimate? How much confidence do I have? 0. It's a 0% confidence interval. What you want is confidence. And you can play the same game as you do for estimation. You can actually solve for the confidence. In this class, I'm just going to give it to you, especially today, because I want you to look at this. Actually, it covers, the confidence interval covers the sample so that a two-sided test would never reject any of those values. See, it's like you have this sample, right? That's the block. We have the sample values. Theta hat's right in the middle. You can't reject that hypothesis. Well, then how far can you go out and not reject? And level out on a two-sided test. So you're never going to reject this as a null. How about this? You're not going to reject that. How about this? How about that? How about that? How about that? Eventually you'll reject, right? Well, you can solve that equation when you know when you're going to reject. And that gives you your confidence. Okay, now I like a class rule for confidence intervals, all right? There's a sign command on Minitab, there's a sign command in R. I don't know, we'll talk about one of them tomorrow, or Tuesday. And when we do that command, it will give us our confidence interval. If you're doing a project or something, that's fine. But if we do things in class, or even if you want to do things by hand, it doesn't hurt to do things by hand on small samples so you know exactly what you're doing. I'm going to give you a rule. Now, the point estimate was the middle. These are just order statistics too. It's actually this. This is actually the asymptotic. And that's fine for class. You know, that's what we did for our p-value. We just used the z approximation. So this is x of n over 2. And then c is this value. It's n over 2 minus a half. Minus z alpha over 2 times square root of n. And this is one minus alpha times 100%. So this goes for 95%. Right? And z alpha over 2 is 1.96. N is 30. Use the full sample. There's no subtracting out values for estimation of confidence. So it's 30 over 2 minus 1 half minus 1.96 times the square root of n over 3. Now this comes out to 9.13. That 1/2 is like the continuity correction, so you've already corrected it, so just round it to the nearest integer. So this is going to be rounded to 9. So then my confidence interval will be the 10th order statistic, right? And then out to the 20th. No, out to the 21st. That'll be my confidence. And then I can just go back to my stem leaf plot, or I could sort the data. Yeah, I could just pick those off. Got 11, so the 10th would be 88. And the 21st would be, the 22nd would be 119, right? 24th would be 1 That's my confidence. Okay, so now we have a complete inference with the scientists. We have testing, we have estimation, and we have confidence. Any questions on that? That's, the rule is in the book. And again, I would suggest these things are easy. What the hardest thing is sorting the data. If you do a stem leaf plot, it's true. Okay. Now, there's one other thing I want. The problem with this confidence interval. Scientists like symmetric confidence intervals. Actually, I do too. I'll use this one. But I wouldn't mind a symmetric one. See, this is not symmetric. You've had normal theory, right? You'd probably use a T. talk a little bit about this. We will talk about number 3 methods in this class, just for parameters. See, this is the standard error of the estimate, and this is the critical value. So the formula is an estimate plus or minus a critical value, or what would you call it, times the standard error of the estimate. Almost all the confidence intervals you did in your basic elementary stat class were this form. Right? They're nice symmetric intervals. In fact, many scientists use what? What's that in? I cover that up. What percent is that in?
90.
It's 95. Just one standard deviation, it's what? 68%. It's just the empirical rule. And you'll find you'll run into many scientists who use this. They just want the standard error, and then they do a 68% confidence interval, right? I want that here. I got the estimate. The estimate in this case was 101.5. I want Z critical value here. And I want the standard error. Okay, it's in the book, and we'll certainly talk about it on Tuesday, but you can do some problems just look at the book. There's a formula for it. Okay. This is all good news if you like non-parametrics. I mean, when I took my first non-parametrics class, I was so sick of the normal something. And I was delighted with the sign test, but then on Tuesday, we'll talk about the head. Well, you probably want to do something else. I don't know what to do about this. I'll call them, but I